This is work I did together with Josef Svenningsson, mostly while I was still at Chalmers. I've now moved to Indiana. So there's an unfortunate thing up there. Good. So at Chalmers we developed embedded domain-specific languages for high-performance array program. So that led to 2 languages so far. We have
a little bit.
Sure.
Thank you.
That's led to 2 different languages so far. Obsidian and Feldspar. We use Obsidian for programming GPUs. So we generate CUDA code from higher level descriptions in Haskell. There's still, when you program in Obsidian, you still see GPU specifics leaking up to your programming model. Feldspar, slightly cleaner language, more elegant. They generate C code, and I think they have plans to target this parallel board and other things. So that's part of the Chalmers ROFP project, or resource-aware functional programming. I'll start with an example, and this is a Obsidian example. So if you just look at it first, it's a bit messy because there are GPU specifics leaking up. Much of it in the types there. So we just remove those. And one thing that Feldspar and Obsidian share are 2 kinds of arrays. And you can see that this is a function that takes something called pull, and it returns something called push. And those are the 2 array representations that Obsidian and Feldspar share. The thing I want to show you in this program is what happens in the body here that implements a reduction. So the input array is split into 2 halves by a half function. So the input array here is a pull array, and that gives you A1 and A2. And the important thing is that A1 and A2 are not represented in memory in any way. They're just 2 new different ways of looking at array, at the input array R. The next step performs a zip width of those 2 halves, and still there is no intermediate result here placed in memory. After the zip width, in Obsidian there's a function called push, which takes a pull array and turns it into a push array. And this is also done without using any memory. But what happens here is that an iteration scheme is imposed onto the array. And first at this point, force, the whole computation is realized and the data is written to memory. Then we recurse. That implements reduction of a array of length power of 2. So what is a pull array? Pull array is an object that has 2. You have 2 operations on it. You can ask for its length, and you can get the length, some kind of integer. It also have this function that you can give a value, and you will get some kind of result, a value of type A, which is this indexing function applied to that index. Push arrays are different, slightly. They still have a length, so you can poke them for their length. But then it has this fill, which is a monadic computation. So fill accepts some kind of mechanism to write that writes an element to memory or does something to one element. What you do is you provide fill with this mechanism that operates on one element, one index element pair, and you will get the computation working on many. So this is what it looks like in Haskell code. Pull array is just the length and the function, and in the push array here you can see what that write mechanism is. It's another monadic computation taking an index and an A, and the result then processes all index A pairs through this write function. So these two array representations have a bunch of properties. When it comes to pull arrays, the consumer is responsible over iteration over the array elements that it is interested in. When it comes to the push array, the producer of the array decides what the iteration schema over that array is, and the consumer just has to obey that. There are some more properties. We have fusion of operations on pull arrays. We have fusion on push arrays. We can implement parallel versions of these arrays. We have efficient indexing on pull arrays, but not on push arrays. And this is because the only thing you can do to push array is give it one of these write mechanisms, and you will get all the elements. So that means you have to go through memory. You have to write the array to memory, and then start looking at the one you are interested in. On push array, however, we can implement efficient concatenation and interleaving, which we could not on pull arrays. The most important property of push arrays and pull arrays is fusion, and guaranteed fusion. Like, if you have a sequence of operations on pull arrays, they are guaranteed to fuse. You have to explicitly say that they should not. And the same for push arrays. You can also convert between push and pull arrays. You can convert a pull array to a push array, and that works very well. Like this example, for example. If you map G, convert to push, map H over some input pull array, this will completely fuse. There will be nothing written to memory at any point. However, it does not work so well in the other direction. So you can, and it's this function that we can't really implement without writing the whole array to memory and then creating a pull array that indexes into that specified memory allocation. So that brings us to the experiment that me and Josef performed, and that is we want to see if we can find an array representation that has yes along that entire column. Yeah. And we performed that experiment in a simple framework. We have a small code generating embedded domain-specific language that generates intermediate code that has memory allocation and reading, writing, for loops, expression language, and then there's a monad for compilation into this intermediate representation. That's the monad called M that you saw in the push array. So the plan is to obtain a deep embedding, push T, that represents push arrays. If we get that deep embedding, we can inspect it, transform it, and maybe this should lead to opportunities to implement new and interesting functions over push arrays. And we chose to approach this via defunctionalization. So how does that work? Here's a function from a push array API. It's map. So map takes a function and a push array. And what we do is we look at the body of that implementation. Functions implemented over push arrays often look a little bit daunting. But what we do is we look at this body, we find the free variables that will become the parameters to constructor. And in this case, P and F are the free ones. So map will have a function valued parameter and a push T typed parameter. And the one thing to point out is that this data type push T replaces this P, not this whole thing. So you can see that there's also a length there, which we don't have access to it here anymore. But that doesn't really hurt us because we can find the length through traversal over this data type. But the procedure defunctionalization also gives us the compiler without thinking. It also comes directly from the body. We just have to do a little tweak here so that the types match up. So now we have a representation of a data type here for push array computations and a compiler for the same thing. And one aspect of this is that we don't need to think at all, and we get the same properties that we had on push A given this implementation of the compiler. We do that for a small push array API with a number of functions. Generate, use, map. Use takes some kind of lower level representation of an array in memory. IMAP, concatenation, interleaving, reverse, rotate. And the result after applying the same process to each of those functions is data type. One constructor for each of them. The compiler falls out also. Just I won't show all of it. So generate and use are in some sense the base cases that you will get to in the end. And at this stage, they impose iteration schemas over the elements. So what does this give us? Well, we now have this tree that we can look at, and so one thing that would be nice is if we could implement efficient indexing, because that was a power of pull arrays and the weakness of push arrays. And indeed we can by just going over the data structure, data type, looking at the constructors. If we want to index into a push T, that's just a generate. We just apply the function that generates the array. If it's map, we need to index into its this push T at index and then apply the function. In use, we need some way to look up an element in memory and so on. And then reverse and rotate. And these two are permutations. So here, indexing would use the inverse permutation of what this one describes in order to go backwards and find the element.
Question. Are you doing some form of rotating on the appends or whatever to get some balancing? Because it seems like this index lookup might be quite slow in the worst case.
You mean in traversal of the tree?
Yeah, is he traversing it down? So if you have a skewed append?
Right. No, we're not doing anything like that. But
So, okay.
You could have smart constructors like this, but
But in what sense is this then efficient indexing? I mean, you've gone from a random access model
yeah,
to a unbalanced tree model, as far as I can see. Is that a fair way of putting it?
I guess so. But we are generating code, and what we want that code to be is it's efficient in the sense that we can pick out one element of the push array without looking at any of the others, at least. So that's like one benefit. And now that we have the tree, we could potentially do other things to it as well. But we have been looking at this very basic, direct benefit of just being able to index. And so what this traversal results in is some kind of expression. And you mean that will grow large if there's an imbalance in the append. Right. So given that we can implement convert from push T to pull, which is very simple, we just use index. And with that, we can implement things that we really could not implement on push arrays, like zip width. So we can now have a zip width function which has push T arrays as input and a push T array as output. And there are more than one way to implement this one. This one uses generate, which gets you an index and looks up in using the indexing function in these two arguments. Another way would be to use IMAP over the first one and indexing to the second one in the body. So how do we evaluate this work? So what we really wanted to see was, can we replace push and pull by something new, and we want to keep all those properties. So we want to see that the compiled code is fused. We want to see that we can write pull array functions on push T, and the code involving index looks more or less like what we get out of the code generator when we have both push and pull arrays. And the first example is fusion, and it really shouldn't be surprising after seeing the compiler that this program leads to just one loop. But I still like to get this concretely in front of me before I trust it. So the point, there is 3 operations composed, but there's just one traversal over the elements. So that's good. And then here we have an example where we implement Saxby, which uses zip width, which is something we would not implement on push arrays. But here we can implement it on push arrays. And the code that comes out looks very much like the code that we would get if they were pull arrays. You may notice that this part is very strange. And it's because it's not compiled onto one of these inputs have a permutation applied to it before it goes in there. And that's to show also that that permutation is inlined into the body there, so it's fused. Then discussion. I think we have more or less yes with modification. We can still write programs that lead to inefficient code, and now we also have the tree traversal issue. But we have one representation at least, and if we program using what was originally push array functions, we get what we would have gotten before, and if we start using pull array aspects, we get also what we got before, but now with only one array type. So we haven't improved anything, but we decreased the size of the burden on our programmer. Extending the API is harder. It's not just about adding another function over push arrays. For example, we need to add another constructor or redo the whole operation. We had to limit the API to forbid user-defined arbitrary permutations. And I think that's the end.
Let me make the devil's advocate for a moment.
Please.
You identified that you need 2 kinds of arrays. Now you figure out that either kind is not good under all circumstances, and in the end you figure out that this is the way you really want to do it. Doesn't that merely show that the distinction of the 2 kinds of arrays, push and pull, was A, artificial, and B, not, let's say, the right way to do it?
Well, if it's the right way or not, I mean, I'm not so sure that I could use this, for example, in Obsidian as of right now. We often use push arrays in a slightly more, here everything is very well organized, like all of these push arrays, they touch on every element, for example. If you wanted to be naughty and only write every other element, then you can't do it in this model, but you can in the other one. So it's a bit of a trade-off.
So there are a few no's that you haven't shown.
none of these languages are entirely settled in what kind of API you want to present to the user. And I think maybe that's what we need to spend more time on before really like nailing one array representation down. Thank you.
This work is in the approach reminiscent of work by, for example, Janus Voigtländer on vanishes. Have you run across that one? Just
I had not heard of it.
Okay.
Sorry.
Because the idea also is to introduce constructors, which are basically lazy data structures. That's what you're doing here, and then applying basically at runtime algebraic properties. So, for example, one of the things that I don't know if you're doing that here is like having a reverse constructor, and in this case, reverse applying after dynamic test to a reverse would be executing constant time. And this is a generalization of doing
Right.
constant time appends. This is how it basically comes. So just wondering if that was something.
Thank you. We will
Okay.
we'll look into it.
Can you comment on the difference between approach and REPA?
Sorry, I didn't quite hear you.
Haskell REPA.
REPA.
It looks pretty similar.
You mean the result of our work becomes something that looks like REPA?
Yeah, I was wondering.
Yeah, no, it does. So, at some level. I mean, REPA is a deeply embedded, or it has these operations. Is it deeply embedded? I don't know. But or like accelerate, they also have a set of maps, folds, and so on. And that's the result we got. So, and the resemblance is there.
So I have a couple of questions if
Sure.
the audience. So the first question is so indexing in a push array, is it impossible without or is it hard because you have to run the computation and materialize?
Mm-hmm.
What's the answer to this?
You have to go through. You have to slot in that write function, and all that does is
You have to execute that right function.
it gets an index and a value.
Okay.
So in some setting, maybe you could
Right.
slot something in there that halts once it finds it, but then it's a linear search.
That's right.
Or,
And then the second question that I have is there's a benefit in what you do because you can actually able to now do it without running that monadic function, which is kind of cool. But kind of the cost is that you fixed an API that you think is a useful API. For example, what I want to implement, let's say, array slices. I will be able to write in subarrays. And how do you think? What do you think about these APIs? Like, would you be extending this data type all the time? What are your thoughts if you want to implement more stuff?
yeah, so one point one potential answer is that if you have your API and you start defunctionalize and you build a data type, you may start to find things that that can be implemented in terms of each other, and then you can perhaps shrink it, and maybe you will find something that's small, stable, and that you're happy with. That could be one outcome. But during that experimentation phase, I don't see that there's a good answer to you would expand and.
So there is hope towards trying to find kind of a minimal core like API that you would like to that you feel comfortable with.
True.
Okay.
Maybe I can say something about that. So we're only fixing the push array part of the API from the beginning, and so we can sort of implement any pull array on top of that with this approach. So slicing is the pull operation.
Yes,
So
yes.
that would be easy to.
That's right. Cool. Well, same speaker again.